All right. Any questions before I get going? Yeah.
No.
Okay. So, so in the prerequisite quiz, I said, show me that you've done some functional programming, and some people did, and some people was kind of iffier. So I'll just get going with a very brief review so that we're on the same page. And like I say, I'm going to be using Scala as the implementation language for that. So why are we interested in Scala? It's a good course to have in a programming languages class because it's what's called a multi-paradigm language. It's object-oriented, it's functional, it blends the two, and so when it's easy for us to get in to the language because of its object-oriented nature. We're all familiar with that paradigm. And it just adds on this functional paradigm. It makes it easy for programmers to start in a kind of familiar object-oriented way and then add more and more functional features to their programs. And so that's why it's fairly popular and getting more so every day. It's statically typed, and so the compiler will help flush out type errors, which is nice. And it's called Scala because it's supposedly scalable from simple scripts to the most sophisticated libraries. And that really has proven to be the case. So many times that I need to write some little utility program, I used to write those maybe in awk or some such thing. And nowadays, people sometimes might use Ruby or Python for those things. And I just nowadays always just use Scala. It's a bit of a sledgehammer. It can do so many more things. But it's also really good at reading a few files, extracting some XML, putting it all back together, walking through directories, that kind of very standard scripting-like thing. And since I know it pretty well, I don't have to think about any strangenesses that I might otherwise have to think in those smaller languages. And people have written very large libraries with Scala. And what's kind of nice about it is that those libraries may be internally very, very hard, but they can still be quite easy to use. We may see a little bit of that in this course. So it was invented by this fellow, Martin Odersky at EPFL. And so if, in fact, you go to Switzerland next summer, you might be able to meet him there and shake his hands. It's not the same university where we have the summer school, but they're very close to each other. And it's so sufficiently similar to Java and C++ that I think all of you are going to be able to pick up the basics of Scala very, very quickly. And it works on the Java VM, so it means that kind of the same tools, the same infrastructure that you used to, you can continue using. Right down, one can use the usual IDEs, Eclipse, NetBeans, IntelliJ, they have Scala plugins and so on. And so it's a pragmatic choice for many industry programmers. But that's not what I care about right now. What I care about is that Scala is my easiest way to show you some useful functional programming. So before we get into that, just a few Scala basics so that you don't get lost in the basic syntax. So the types are all written in uppercase. There are no primitive types in Scala, so int, double, boolean are classes. Arithmetic is just like in Java or C++, the same operators that you're used to. The first thing that's kind of different is that when you declare a variable, you declare it with the keyword val here. Thank you. And you don't have to say what type it is. It looks at the thing on the right-hand side. In this case, that's an int. And because 13 is an int, then the variable is typed as an int. So it's still strongly typed. The type int is associated with the variable, but the type is inferred. Semicolons at the end of a line are optional. And so what I find that most Scala programmers, when they first start out, this makes them really, really nervous, and they put in the semicolons. And that's fine. Just put them in. But I don't usually put them in because you look smarter when you take them out. So whatever you want to do. Now, when semicolons are optional, that sometimes gets you in situations where, how does it know whether a line continues to the next line? It can't read your mind. And so what you want to do is you want to create a situation where it would be impossible to end a line. So here I put a plus, and you can't end a line at a plus because there's something needs to be coming, and then that's fine. An opening parenthesis, an opening brace, any of those things will work. So everything is an object. So the number 1, for example, is an object. None of this nonsense that you have in Java with primitive types versus objects. I mean, that might have made sense 20 years ago, but nowadays we rely on the virtual machine to worry about the efficiency of primitive types. So one can take a method. In this case, there's a method called to. So you call one.to. The to method takes a parameter. The parameter is the number 10. And the call, as it happens, one.to of 10 returns an object of type range, which is intuitively pretty clear what it does. And the range contains the numbers of 1 to 10. And so that is kind of intuitive, but it gets much better than that. Whenever you have something where you have a dot, and then the name of some method, and then a parentheses and a single parameter, then you're allowed to omit the dot and the parameter and the parentheses, so that it looks like this: 1 space to 10. And that looks actually kind of nice. So 1 to 10 is this range of the numbers from 1 to 10. Here's write it as 1 to 10. And the rule is very uniform. Anytime that you have an object, the name of a method, and a single parameter, it gets translated by putting the dot back in and by putting the parentheses back in. That's even the case for the expression 2 plus 3. In Scala, you're not limited to alphabetical characters or alphabetical characters and numbers for your method names. You can use any symbols for your method names except for a small list of exceptions, like the semicolon and the parentheses couldn't be in method names. But everything else can. So plus is a perfectly legal method name. And that's in fact what happens. When you write 2 plus 3, the Scala compiler says that really means 2 dot, meaning we're applying the plus method onto 2 with a single parameter 3. So for the Scala compiler, plus is a method. It's very, very uniform. And so as later on, as you might be in the situation that you define your own methods, people like to define some methods, not too many because it gets confusing, but some methods that use some of these operators. For example, we'll later see a method that has this name. And one uses it for expressing maps, where it has a natural meaning. Of course, you could go wild and crazy, and people complain about that. They say, well, Scala is evil. It has these overloadable operators. And nothing stops people from coming up with an operator that looks like that. And you know what? They're absolutely right. Nothing at all stops you. Just like in Java, no one has ever forbidden you from naming a method. So maybe we need a rule in Java that says you must have at least 2 vowels in every method name. I mean, at some point you can't police a programmer, right? You have to rely that programmers use the features that are given to them in reasonable ways and in good taste. And so in Scala, it's the same thing. You're allowed to define your own operators when you need them, and you're encouraged not to do that unless it's actually an improvement. So, but what is kind of nice is that you have this great uniformity here, that once you understand how the parser works, then you can enjoy doing things like 1 to 10. All right, next, immutability. Immutable means that something cannot change. So in Java, we have this all the time. Strings, for example, in Java are immutable. Those of you who moved from C++ to Java, that probably was a surprise. That in C++, it's easy to change a string. You just grab one of the characters and put something else in there. In Java, you cannot do that. So for example, when you call to uppercase, oops, I meant to uppercase, not Java, I think. But when you call to uppercase on a string, then it doesn't change all the letters to uppercase. Instead, what does it do? It gives you a new string, a different string that consists of the uppercase letters without disturbing the original. In fact, it is impossible in Java to modify a string. Why did they set it up like that? Doesn't it sound expensive that every time you want to change a string, you have to make a brand new one?
Maybe type safe.
No, it's still safe.
Uh,
It's defined as fine.
Yeah, but why? What's good about it?
to prevent the stack smashing.
I guess.
We need to get concurrency.
So concurrency for bigger data structures, that's a big advantage, and that's why Scala does that. In Java, the thinking was much simpler. They just wanted to be able to share strings. That if literal strings are always the same, if you can't modify them, then you can just share them. then because there's no difference between having two copies to the same string as long as it's immutable versus two distinct strings. You can't even tell the difference. So, in Java they just use it for sharing, but in Scala we want to use it because we're more interested in concurrency. And if you have a data structure, say a hash table, that can never be changed, then you can have 10 threads looking at that hash table, and they will all see the same thing, always. So we want to encourage doing that. And so what's called pure functional programming, no mutations are ever possible. So there are programming languages in which no mutations are ever possible. Scala is not one of them. There is a way of doing them. I'm not going to tell you how, because I don't want you to use it right now. But so Scala just encourages using immutability. So it sounds, if you've not done this for a long time, it sounds kind of weird. Now, how can you get results if you can't change anything? So here's like a typical example. Let's say I want to write a function that takes an integer, say, 1, 2, 3, 4, 3, and it returns the set of the digits in this integer. So in this case, it would have to compute the set consisting of 1, 2, 3, 4, and then it sees the other 3, but that's already in there, so it wouldn't put it in again. So how would you do this in Java? Well, in Java, you would come up with a java util.set. You would put in the 1, you would put in the 2, you would put in the 3, you would put in the 4. You would probably just put in the 3 and rely on the set to reject the duplicate. But at each step, you would mutate that set. It's a different set afterwards. So that's kind of the natural Java solution. And from that, it sounds hard to believe that you can write this in an immutable way. But in Scala, it's actually perfectly simple. Here's how it works. So the first thing just takes care of a negative number. Now, if the number is less than 10, then I'm returning the set containing just the number. If it's 1 to 9, that's the only digit in there. Otherwise, I divide by 10 and recursively compute the set of that, and then I add to that the single number, that's the last digit. So in this case here, the set would be built up as follows. So if I compute digits, I don't want to use such a long one, so I'll just do 1, 2. Then it'll compute digits of 1, 2 plus the number 1. And digits of 1, 2 is, of course, the set containing 1, 2, and recursively. And then plus 1, it's now going to compute a new set of the result. That's actually not true. It's going to say, well, gosh, since 1 is already in there, I can just use the same set again. I'll just reuse the same set. And so that's what plus does. Plus takes the set on the left, the set on the right, and says, if the thing on the right is already in this set, I'm just going to return the set itself. Otherwise, I'm going to build a new set and put in everything. Now, when it builds the new set, it actually, and we're not going to be discussing that in this course, it does it in an efficient way. It doesn't copy all of the elements into the new set, but the new set structurally shares the old set. They're very clever data structures that are built for this kind of structural sharing. So that would be an interesting course in data structures to learn about those. But you're just going to have to take my word for it that this is actually pretty efficient. And so the reason that we like this is these kind of computations are parallelizable. You can memorize them. So this, the digits function could remember its last 100 results and just give them back to you because there are no side effects. Nothing has changed during the computation. When you call it again with the same question, it has to give you the same answer. So one of the nice things about functional programming is that you call the function again with the same inputs, they must give you the same output. That actually makes it impossible to write a random number generator in a pure way. You cannot write it, right? Because when you call it, you would get the same answer every time, but that would not be very random. So it's a challenge for a pure language. Now, Scala is not pure, but it tries to be as pure as reasonable. All right. So now, why is it called functional programming? We haven't talked about functions yet. It's called functional programming because functions are values. So, what's a value in a language? It's something that you can manipulate in the programming language. In Java, values are pretty simple. There are two kinds of values. There are the primitive values of those 8 primitive types, int, double, short, long, byte, and so on. And there are references to objects. That's the universe of Java values, primitives and object references, nothing else. So there's things that a Java program cannot manipulate. For example, methods. A Java program cannot manipulate its own methods. You can't store an array of methods, for example. You can't have a method that returns another method. It's impossible in Java. They're not part of the Java language. You can call methods, but you can't store an array of methods. In C++, things are a little bit different. You have the primitives again. You don't have references in C++, but you can directly reference structures or classes, and you have pointers. So those are all of the things that you have in C++. In C++, you do have pointers to function, and so you can do some things that are somewhat functional. But a function is not a first-class value in C++ even, because you cannot create new functions in the C++ program. A function cannot return a new function. It can only return a function that was already compiled. In a functional programming language, on the other hand, functions are like numbers. Functions are first-class citizens. You can have an array of functions. You can have a function that computes new functions. You can have variables that hold functions, and so on. So in Scala, here's how it looks. I have a val that contains 3.14. You have another val that contains a function. The way you write a function literal in Scala is a little odd. You have to, in this case, it's the name of a method, the math.ceiling method, followed by an underscore. For technical reasons that I don't want to get into. If you just put math.ceil, it says, oh, you want to call me with something, and it gets confused. The underscore says that you actually just want the function. Kind of like the ampersand that you might use in C++. So now fun is a value that stores a function. Just like num is a value that stores a number. Same thing. Now when I call fun of num, it empties out this value here. It says, oh, that was a function. It empties out this value here and says that was a number, and the parentheses mean call the function. So numbers in programs can be anonymous. If you write the number 3.14, that's just the function, the number itself, 3.14. It has no name. It's not called pi or anything. It's only called pi when I put it into a variable called pi, which I wouldn't do because pi is actually 3.1415926, whatever. But so it's just an anonymous little thing here. And you can do the same thing with functions. So here I have a function that I don't bother to give a name. And what function is it? It's the function that consumes an x and produces x times x. That it doesn't have to be called square. It's just a thing. It's the squaring function, but I just don't happen to give it a name. And sometimes you have functions that don't have nice names anyway. What about what would we call it? I can't think of a good name for it, so why give it a name? You can just refer to it by what it actually is. So you can take this function, or the function squaring function, and you can store it in a variable. Just like you can take any number, literal, and store it in a variable. So there's no difference between numbers and functions. Functions are values just like numbers are. And that's what makes a functional programming language. The functional programming language is a language where you do not differentiate, where functions are nothing special. Functions are values like anything else. You can manipulate them. Yeah?
Just a quick question.
Yeah?
You said math.ceil. Why do you mention underscore just to differentiate that it's a function?
Well, if you just write math.ceil without it, the compiler will say, I'm missing an argument. Then it's if you want to compute ceiling,
Give your mouse away.
I'm still. To call it, you would say math.ceil of 3.14, say. Or you could even call math.ceil 3.14 because you're allowed to omit the parentheses. And so when it just sees math.ceil, then it thinks that you're going to be delivering an argument to it next, and it gives you a syntax error when that argument is not coming. And so to make it, to say, I just want the function, you have to put the underscore. That's the syntax that they chose to deal with this parsing difficulty. We don't often run, well, I shouldn't say that. I shouldn't say this. It does happen once in a while. Usually what happens is I boldly write math.ceil and I forgot all about the underscore. Then I get an error message that says you're missing your argument, and then I say, oh, and then I put it back. What's that? There's not one slide showing up. All right, so why do we care? The reason we care is that it's often useful to pass functions as parameters to other functions. So for example here, I'm having the range 1 to 10, and now I call map. Map takes a function and applies it to every element in the range, and then it gives me a collection of all the answers in one fell swoop. So over here, I get all of the squares at once. And what we've had in the prerequisite quiz, I was trying to get at filter. I don't remember what it was, but you were supposed to filter something up. You were supposed to look at all of the things that fulfill a particular criterion. And so a functional language has something that's typical of filter, so it's called a Scala, where you give it a Boolean function, a function that's true or false, and it gives you all of the ones that fulfill this. And so it gives you this whole collection again. So map just applies a function, gives you all the answers. Filter takes a Boolean function and gives you all of the ones that pass. And then there's finally for each. For each takes a function and just executes it without giving you an answer. So you would use for each if you wanted to print something where you're not interested in the results. So these are kind of the bread and butter things that you use in functional programming, and it's very common to have expressions where you chain together maps and filters and another map and another filter to manipulate some set to get an answer. So in fact, Scala programmers take this as a point of pride to take something that looks like a really complicated computation and turns it into a sequence of maps and filters. So in C++, we could implement map actually. So here you'll find an implementation. In C++, you can implement map with function pointers. C++ programmers don't do this very often, and the reason they don't do it very often is that it's awkward to use. In C++, how would you call this map thing? You would have to, you can't have anonymous functions. You can't just pass in the function that you want, but you would have to put it elsewhere and then reference it by name. And for short functions, that just is no fun. And so you could do it in C++, but because the language does not have anonymous functions, it doesn't lend itself to it. That will actually change with C++ 2011, where they are giving us anonymous functions. So it's possible that C++ programmers are going to embrace this style much more. So in Scala, a function can also return a function, and we'll see examples of that shortly. So here I have just a simple examples. So I want to remove all 0 values from an array. So yeah, or from an array list, because it's too hard to do it in an array. So I have an array list, and I remove everything that's 0. So how do I do it? I step through the array. If it's 0, then I remove it. So there are two problems with this solution. First of all, it's actually not very efficient, because when you remove the first one, then it slides all the other ones. Then you remove the next one, it slides all of the other ones. And so you should be doing it from the end. And the second one is, it's actually wrong. What's the bug?
The size will decrease.
Yeah, the size will decrease, but that's okay because a.size is a method. It gets called every time. If I had put a.size into n, then that would have been bad, yeah?
When you remove the item,
Yeah?
the loop, it will iterate less number of times.
Yes?
So that's the bug.
Yes, it'll skip the next one. So if you have 2 zeros in a row, it won't see the second 0.
So to store the size in some separate variable and
whatever, right? And so to actually to get this done right takes more than a couple of minutes of thinking for most people. But look at it, how trivial it is in a functional language. You say, you just filter by the ones that are not zero, and you get the answer. It is trivial. All you have to come up is you have to dream up the right function, and you have to see that you have to use filter. So, so that's the selling point for using functional language. And it takes a bit of retraining oneself, if you've not done that, to look at problems in a different way. So nowadays, whenever I see that kind of looping over a collection and transforming it in some way, I try to think about it as how can you use maps and filters to achieve that goal, as opposed to writing an explicit loop. And it's totally amazing how often that not only works, but it gets you code that is shorter and that is more demonstrably correct. Because in the end, when you look at a lot of loops, once they get past the 3 or 4 standard loops, loops are fiddly things. It's easy to get something wrong with the indexes and so on. So the functional solutions are generally easier to read. They may be less efficient because it has to build up some intermediate data structures, but that's something we worry about. Let the optimizer worry about that. All right, so that's the basic pitch. So let's get into this lab so that we do some interesting stuff right away. So we're going to be doing the labs in groups of 2, and so maybe the 2 of you could work together. Maybe the 2 of you can work together. You already sit in 2s. They have 2 here and then 2 there. And that kind. Now, do we have 1 left over? And now we have 1 group of 3, huh? Well, I guess then the remaining ones of you are just going to be a group of 3 for today.